Welcome everyone. So what's on the agenda today? We will talk about a methodology called Design for Assembly, and I will do this in 3 different sections. So in the first section, I will introduce the concept of Design for Assembly and explain the why, the what, and the how of this methodology. Then in the second section, I will explain how we at Vlaanders Make applied this methodology on a real company case from industry. And then finally, in the third section, I will go over the Vlaanders Make Design for Assembly offering and will explain how we can help you to improve your design process. So let's get started with the beginning, the why, what, and how of Design for Assembly. So first of all, I want to explain a little bit the context of this talk. It's about bringing a new product into the production. So it's a development process of a new product. And usually this process can be shown as this. So you start with your requirement gathering, then you do some concept designs, then you go to a detailed CAD design, then you do some optimization and get a finished CAD file, and then it goes to the production engineering department, the production planning, and then finally your product goes into production. And since this is a very complex process, it's usually performed by multiple teams. So the first team is a design team that consists of designers and design engineers. They will focus on the first stages of this process, the requirement gathering, concept design, detailed design, and finished design. And they work in a virtual world on the computer. They can use CAD tools, optimization, and simulation tools. Of course, a design is never first time right, and some iterations will be needed to come to the finished design. But since they work in a virtual world, these iterations are very cheap and easy to perform. Once they are happy with the design and they could meet all the requirements of the customer at a reasonable price, they will hand over their finished design to the second team, which is the production team. The production team consists of production and process engineers that want to plan out how this product can be efficiently manufactured in the factory. They will focus on product engineering, production planning, and finally monitor the production of the product. They are in a physical world and have to do real physical prototypes of the product and also do tryouts with operators. So when they have to iterate, these iterations are already more costly than the iterations in the design process. And in some cases, the worst case scenario, they even have to iterate together with the design team since there are big problems with the manufacturability of the design, and this type of iterations are the most costly. So Design for Assembly has as a target to avoid these iterations. So we want to reduce the costly iterations as much as possible, and ideally we only have the green virtual iterations that are cheap and fast to perform. And so the main benefit of the methodology will be that your production development process becomes faster and cheaper. The second question is then, how do we achieve this goal of avoiding these iterations? And there, the Design for Assembly is a methodology that will capture the production concerns of the production department and try to front-load them to the earlier stages, in this case, the design process. So it's a formal method to do this front-loading of production concerns towards the designers. And how do we do this? It consists of multiple steps. First, we need to start at the production site and capture their needs. So we will have to formalize the production processes. We will need some cost and time models to estimate how difficult it is and how costly it is to manufacture certain products. And we can also gather a history of past issues so that we can avoid them in the future. When all these concerns are properly formalized, we can bring them to the designers, and there are different options to do this. So the 3 main methods to bring this knowledge to the designers is either through guidelines, which inform the designer before they start designing, axioms, which restrict the designer during the design so that they can only design products that are assemblable or manufacturable, or through rules that evaluate the designs during different gates in the design process. So in summary, the Design for Assembly will formally capture the production concerns and convert them into guidelines, axioms, and rules for your designers so that the production concerns can be considered during the design phase. In the next few slides, I will now go a bit deeper in each of these 3 methods and explain some examples of these methods and the pros and cons of each of these approaches. So for design for assembly methodology, we will start with the most simple approach, which is guidelines. So actually just inform your designers about the production before they start designing. Some common examples of guidelines are to reduce the product complexity. So often designers are shown two possible cases, a complex design with a lot of parts and a lot of connections, and then they are emphasized to create a more simple design that has the same functionality but has far less parts and connections needed to be made. Another guideline that is often given is to use standardized parts. So try to reduce the variety of parts, especially common parts like fasteners in the design, and use fasteners from the same standard so that there is a benefit of scale in production and the design can be made cheaper. And then the third category of common guidelines are these historical examples or cases where there is a bad example and a good example of a certain design. For example, to emphasize the visibility, the insertion of tools, the stability of subassemblies, and potential misplacements. So for example, can the operator use a tool efficiently when he has to fasten a certain part? Can a part be inserted in a guided way, or is it more difficult, and does the operator have to feel how to insert the part? And does the shape of the part reflect how it should be added to the assembly, or can the operator make a mistake and mount the part in the wrong direction? If we now evaluate this approach of the guidelines on different criteria, we can see the strong points and the weaknesses. So the different criteria are the ease of adoption. How easy is it to add guidelines to the design process? How much does it restrict the freedom of the designers? How easy is it to update this methodology? How traceable is the methodology? Can we really measure the effects that it has on the whole process? How formal is it? Can it be interfaced with CAD tools? How accurate is it? Is the assessment always good, or can you make mistakes? And how fast can you apply the methodology? So when we look at guidelines, the strong points are that adoption and the freedom of the designer are really good. It's easy to adopt. You just have to give a workshop to your designers. They're informed, and then they are still free to apply it however they want. On the fact of updating the methodology and executing it, it's hard to really measure how efficient it is. You could give a second workshop if you want to change your guidelines, but you're never sure if they really follow the new guidelines, or in their mind they're still considering old, outdated guidelines. And also for the speed, it's hard to judge how fast these guidelines can be addressed during the design process. And then we come to the worst case scenarios. So traceability, formality, and accuracy is rather low with guidelines because they're just rule of thumbs and they're very subjective. There is always some expert knowledge needed, and you don't really log when you apply these guidelines and when you forget them. So this was the first methodology. The second one tries to correct the weaknesses of the guidelines, and it's called Actionable. So it's really restricting your designer during their design process. This can be through limiting the libraries that they can use during the design, or by providing them with automated tools in the CAD software to generate parts of the design automatically, so that you are sure that they consider the right production considerations during this generation. Or the most extreme case, just stop with freeform design and start using configurators, where you just give some requirements and then the tool automatically generates a design according to these requirements. When we evaluate this approach, the strong points are clear. They try to correct what was wrong with the guidelines. It's very formal, it's very accurate, and it's fully automated, so it has a high speed to be applied. But of course, this comes at a cost. Again, the traceability is not that clear because it's a bit an everything or nothing approach. You know that you follow the axioms, but you don't really easily can measure the impact they have and if they really prevent problems in production or not. And then on the front of adoption, freedom, and updates, this approach scores very badly because there is a high development cost to make these automated tools. It's also a high cost to update them if your processes change. And usually designers are very hesitant because their freedom in the tools are very restricted. And the new tools, they're also very technical and they have to learn an extra tool. Then the third method is the rule-based method, who says, okay, the designer is free during the design phase, but before going to the next phase, there is a checklist of rules that needs to be evaluated, and only if the design follows all the rules, it can go to the next stage. So these can happen in different forms. It can just be a paper checklist that during a design review is checked off by an expert designer that looks at your CAD file. Or it can be based on cost and time estimates to make a given product with a data-driven tool, like, for example, the DFA tool of Boothroyd and Durst. Or it can even be one step further, a full automatic evaluation of design rules, which is already common in PCB design. And also there already exist some tools in the mechanical CAD world to also apply rules on a CAD file in the tool automatically. So when we will evaluate this approach, I will first start with the far left, which is just the paper checklist of the rules. If we then look at the strong points and weaknesses, we can see that again for adoption, it scores very well because it's very low effort. You just need a piece of paper and you also can easily update it. You just update your rules on the paper, and in contrast to the guidelines, it's traceable. If you keep your evaluations, you can easily see what you checked when, and if that prevented a problem in production or not. Then the intermediate scored points are, of course, the freedom is a bit more restricted than with the guidelines, but not as much as with the axioms. And then on the formality and the accuracy, it depends a bit. You still depend on an expert judgment. So it's not as good as with the axioms, but it's still better than with just following guidelines. And the main weakness of the approach is actually the speed. You need an extra process, a review process, where you need valuable time of an expert designer to evaluate this checklist. So if we then move towards the more automated approach, the far right, and we update our evaluation, then we see that the picture gets much better. So formality, accuracy, and speed, since it's an automated process, are very good. The updates are still a bit tedious because you have to reprogram some rules in this technical program, but we see in practice that remarkably, the adoption of this type of tools is very low in industry today. And so that's a bit the goal of this session, is to show the value of tools like this and how they can be adopted, and how Flanders Make can help you with adopting these automated evaluation of design rules for assembly. So this was the first part of this Tech at Lunch. It was quite technical. It gave you a broad overview of what the method entails. Now we will make it more specific, and I will zoom in on a concrete case that we had during one of our projects. So the case presented here is from the company called Alberts, and they make these smoothie vending machines. So it's a machine where you can pay for a smoothie, and you can also choose the recipe that goes in the smoothie. And it actually has to crush frozen food or vegetables to add it to the smoothie. So in each of these machines, there are 10 subunits, which are called the crusher units. It's very simply said, just an engine with a set of blades that help you crush the fruits or the vegetables. And they make these units, or they assemble them fully manually. And their question to us was, okay, we are in the process of redesigning this crusher unit. It's quite a critical unit because there are a lot of them in one device. And we wonder if we can improve our design to facilitate the assembly process of our crusher unit overall and of the machine. So how did we tackle this problem? So first of all, what inputs did the company Alberts provide? They gave us a CAD file of their product, in this case, the crusher unit. We visited the site and they explained to us how they do the assembly process at the current time. And they also gave us an assembly sequence in the form of work instructions, but this is an optional input. And then with this input, we started applying the methodology that I explained, the design for assembly methodology. So first we checked the CAD file if there were any drawing errors. It's like a pre-processing step to make it ready for our tools. Then we also inserted the assembly sequence that we could find in the work instructions. We digitalized it and added it to our tool. Then, together with Albert, we identified the relevant assembly rules for their process and their product, and then we automatically evaluated those rules on their CAD file for the given sequence. And what did they get out of it? We presented to them the list of rules that they can still use also manually in their development process to check their designs or new designs of the crusher in the future. We gave the detailed output of this evaluation, and we also, together with them, came to some actionable insights on how to improve the product design, the sequence, or the process. And to clarify this a bit more, I will now go a bit more in depth in each of these outputs. And so the first one will be the design rules. So we have a portfolio of design rules. There are 7 in total. So there is a rule about detecting and counting the number of standard parts in your design. There is a rule about misplacement risk. Can a part be placed and connected in the wrong orientation? In other words, is there a risk that an operator makes a mistake? We have a rule that evaluates the insertion and usage of tools to attach fasteners. We have a rule that checks weights and sizes of subassemblies so that in each stage it can be guaranteed that the subassembly stays manageable by an operator. We have a rule on gravitational stability that highlights when parts need extra support. We have a rule on the visibility of the parts and if they can be seen when working on the connections. And then we have a combination of rules on insertion of parts and insertion path of parts that can evaluate if a part can be inserted and if so, which path it should follow to be inserted in the subassembly. So this is more or less the whole portfolio of the rules that we currently have developed. And then together with Albert, we decided that only these 4 sub-rules are relevant. So the misplacement, the tool usage, the gravitational stability, and the visibility rule. So that was the first output, finding these relevant rules and explain to them how they can evaluate them. Then the second output was this DFA report. There are 2 levels of detail of the report. First, there is the overview level. And so in summary, it can be represented as this. So what are we looking at? It's actually a simplified representation of an Excel sheet where the rows are the different operations in your assembly sequence. So here it's like you start with the engine, then you add a connector part, you add a coupler part, and so on until you assembled the full crusher unit. The columns are the rules that we just selected. So it's again gravitational stability, tool usage, misplacement, and visibility. And then in the cells, you see a color-coded score of the evaluation of this rule. So green means that the score is good, and more towards red means that the score is bad and that there is a problem. And this gives you a kind of a heat map, so you can easily identify which parts or which operations are problematic. For example, if we look at the second line, the connector, we can clearly see that there is an issue with placing the tool and with potential misplacement risk. So we know there we have to have a closer look. Similar for the shaft and for the grill and the shaft holder, we see some problems with stability that we need to investigate. And we also see in the misplacement column, the third column, this green-yellow alternation. And this shows that every time there is a knife in the operation, there is also a potential risk of misplacement. So this is the overview. And then for each cell, our tool can also generate a 3D visualization of the problem that it identified, such that designers are supported with the redesign or solving this problem. So in this slide, I will show some of these detailed visualizations. For example, for the gravity rule, we can show the contacting surfaces and we can highlight the parts that are considered unstable or unstable by the algorithm. If we go towards the tool rule, we can show the tool in position and its range of motion, and we can highlight which positions are colliding with other geometries. And that way we can see if the tool can be efficiently used or not, and which parts are blocking the tool and need to be changed. And then with the misplacement rule, we can show the correct positioning of the part, with also a list of possible mispositionings in red in this case. And the more of these red positions there are, the higher the risk that an operator will choose the wrong position and make a mistake. So this is a type of feedback, visual feedback we can give to the designer in order to come to solutions to the identified problems in the sequence. And this brings us then to the last output, which are these actionable insights. So in case of the Alberts company, it helped them to redesign some parts, for example, a redesign of the blades so that they are more difficult to be misplaced, a redesign of the connector part so that there is more visibility and more accessibility for the tool, and also some updates to their work instructions to warn operators for potential problems related to misplacement, and also to encourage operators to use the tool in the right orientation so that they have a full range of motion instead of a restricted range of motion. So this ends the second part. I hope it made it a bit more tangible what we mean with these design for assembly rules. And in the last part, the third part, I will go a bit deeper about the competences of Vlaanders Make and what we can bring to your company if you're interested in applying this methodology. First of all, it's important to emphasize that this is not a very new result, but that this is the result of a lot of years of research. So we started with a PACO SBO project, then continued within the Assisted TFA ICON project. And so in total, we already worked on these results for 8 years. And of course, this means that the results evolve through time. So in the SBO, we started just by a console-based tool, a lot of Python scripting that could process files, but it was not very visual. Then we made a transition to a FreeCAD workbench, which gives a user interface and allows us to generate these visual feedback images towards the designer. And then at the end of the Assisted TFA icon, together with BricsCAD or Bricsys, who develops the BricsCAD mechanical software, we did a transfer of our IP to their software, and they integrated our algorithms to extend the functionality of their tool. So now today there is the FreeCAD workbench, but there is also a commercial release of our algorithms. Oops. So what can we, Vlaanders Make, bring as an offering? The first one is just the knowledge about the methodology. Like in the beginning of this session, we have knowledge about production design and the development process, and we can guide you through the state of the art, so the academic literature, but also the commercial tools that are currently available. And we can check, is what's already available sufficient for your company, or do you need more custom solutions? And if it turns out you need more custom solutions, we can together with you set up the right set of rules specific for your process and your products. We can do an evaluation for you to see if these rules are workable and what insights they can bring. And we can also support you with integrating our algorithms into your CAD software. And in that last part there, our IP is also involved. So we have IP for a library of CAD-based DFA rules. And we even have our FreeCAD prototype tool that also has a user interface and more visual feedback towards the user. So based with this expertise, we have actually 3 different offerings. The first one is a DFA workshop where we just come to your company, assess the situation, and organize some sessions with your designers and with your production team to establish the design for assembly methodology in your company. And the price is around €500 per person that follows the workshops. A second offer is the evaluation as a service, a bit similar to the case of Alberts. You just provide your product CAD file, you provide some information on the process and the sequence, and then we can do this detailed DFA analysis. And there the price per 100 parts is around €10,000. And then the third offering is actually helping you with integrating these CAD-based tools, these algorithms, into your workflow, so into your CAD software. And there, per algorithm, we count around €30,000 per algorithm that we need to integrate. So this is what we, Vlaanders Make, could bring to your company. So usually if I present this slide and I go to a company and I show, look, this is what we got, this FreeCAD workbench with design for assembly rules, there is always some skepticism. And so the remainder of the slides is there to tackle some of the common questions. So usually the company says, nice research, but do I want to pay for this result? And then we come with the 4 main benefits towards the company. So it will improve and make your review process of your products faster. It will improve your product development process. It can even improve the assembly process itself, and it will allow you to capture and formalize knowledge within your company. And then they often ask some extra questions on these 4 points. So we say it's faster, but how much faster is it compared to just applying the guidelines or applying the rules by hand? And for that, we did the assessment with the same case from Albert's. So there we had 4 rules for 18 parts, and we said, okay, if you have to evaluate these rules manually, it's 5 minutes per part per rule. So we came to 360 minutes in total to do this assessment fully manually if you fill in each of the cells in the Excel. While with the tool, the evaluation of a single cell is twice as fast, so we only count 2 minutes, but there is even more acceleration possible because the tool can compute in parallel each of the rules. So in this case, we divide it by 4 because we can evaluate each rule in parallel. So we go from 36 minutes, 30 towards 36 minutes. So from the 360, that's a reduction of 10. So that's a big speed up that you can have by going really to the automated tools and not just do the methodology manually. So then they acknowledge, okay, it's faster, but what can it bring to my company? Is it worth to invest? And there the answer is a bit more difficult, but we have some guidelines to help you to envision a return on investment. And so the important questions to ask yourself is, how often do I bring a new product into production? If that number is sufficiently high, it already highlights that there is a potential for these tools. And then per product, how much time do I spend on product reviewing? How high is the cost for the prototyping and the tryouts in the factory when I bring the new product in production? And how many of these costly iterations, assembly problems do I have currently today in production? If all of those things are high, then we are quite confident that when you adopt these tools, there will be a clear return on investment. If you only bring 1 product a year into production, then probably this tool is a bit overkill because the potential gains are not worth the effort to adopting this new technology. And then for the last part, we often get the question, okay, knowledge formalization, that sounds a bit academic. What is it worth for a company? And so there we also have 2 examples. One is knowledge loss that you want to prevent. So if you have retiring senior designers, they often have a lot of experience. They build internally their own guidelines and rules, but it's all in their head. So if they leave the company and a new junior designer joins, all this information is lost. While if it was captured in the tool, you could just hand the tool to the junior designer and they are up to speed immediately. A second reason is, okay, maybe you know your current processes very well, but you are planning to start producing for new processes, new forms of automation, or maybe 3D printing. And in that case, it could be that your designers are not yet familiar with these new processes, and then through adoption of these rules, they can immediately learn on what they have to pay attention when they design for these new processes. So it can also help you to gain knowledge that you don't have yet for the future technologies. So that concludes the 3rd part of this presentation. So we're really almost at the end. I still have 2 more slides. So first of all, a summary slide. So what did we talk about? We talked about the problem of the costly iterations in the product development process. I explained to you that a CAD-based design for assembly evaluation can be a solution to prevent these costly iterations. I explained or gave an overview of the DFA offering, so the workshops, the CAD-based tools, the evaluation as a service, and our IP licensing options. I highlighted the added value that these tools can bring to your company. And when our target groups are not limited to assembly companies, we also want to work with design and engineering agencies and even the service tech providers that work around tools related to CAD and product design and development. And then the final slide, I hope this was insightful and inspired you. So if you're interested in these tools or these services, you can contact either me or my colleague, Bieke de Kramer. And of course, I also want to thank some people. So first of all, our industrial partners, Alberts and BricsCAD, who are willing to let us share the results that we got with them in our project. But of course, also all the other companies we worked with during these 8 years of development. And then also the whole team, so it's not a one-man show. These tools were developed by a whole team of researchers at Vlaanders Make over the many years. So also thank you to them. And then finally, to conclude, this is one of the results of the team that is called Design Techniques, but we also have other results in our portfolio. So even if you're not interested in design for assembly, you can always reach out to us for these other topics as well.